Hi, so let's continue with our videos. So we have talked about this. So these things. So we talk about free vibration, which is called friction damper. So this is the topic. So as we already mentioned, and this is the damping coefficient C. Okay, so it's Newton second per meter. So the situation is that we have to still go back to this one. So when you solve any spring equation or homogeneous or non-homogeneous, the first thing you have to do is to understand the movement. So for this case, you have to understand how these things move. So meaning if you were to put this mass down, okay, if you put this mass down into this some position over here, and you release, the spring itself will oscillate. But however, the oscillations, the amount of oscillation is dependable of the damping coefficient of this damper. So if the damper is kind of strong, you'll actually prevent oscillation from very vibrative. So you'll not oscillate like that. So you oscillate like very slowly. When you release, you oscillate, and you will not oscillate, but rather than going back to its original position. So apparently, this damper is a very useful material. And one key thing I want to make you um I lost my words. So yeah. So I just added this thing. So in this portion we need to remember the application. So I think the test may come out just ask you the applications. What is the application? So it's to use to slow down motion. So imagine you have a door, and then the door, when you close the door you slam, right, whatever. But however, the damper itself will actually slow down the motion of the closing of the door. So this is you have to take note. Slow down motion is a keyword. And then derive general equation. So you have to derive manually the general equation. So what do I mean by, for me, for okay, this manually is just for me lah, okay, not for you. But I just want to let you know, and then how to derive it. So let's go back to this. Is the We have to understand the movement. So you already understand the movement. So we have to draw the free body diagram. So this is the free body diagram. Yeah. Okay. So apparently, one another key thing to take note over here is that free body diagram um describes what are the forces that acts on the mass itself. Okay. So maybe I should write down over here. Free body diagram describes what are the forces that acts on the mass itself. Okay. So in this case, maybe I should state over here lah. Okay. But anyway, so what does this mean is that when you pull this down, there will be a certain displacement x, velocity and acceleration, right? There will be all these three going down, and then there will be a, a coefficient cx, okay, because the damper itself has a certain velocity, okay, with a damping coefficient times its velocity, okay, but I don't know why it has velocity. So yeah, but anyway, it's this motion, and then kx is the spring constant times the displacement. And then once you know this, the next thing you need to do is to you know get the VE. So meaning the convention. So going down is actually addition. Okay. So with this set, maybe I should draw the picture out. Okay, so our free body diagram. First step is to define free body diagram. Second step is to say that we define our VE as the convention is going down. And then number three is to define the spring constant times the displacement. This is step three. Step four is to define the damping coefficient. The reason why this is minus, okay, is because the x itself is going in this direction, right? Because V is plus, but we are going the reaction force, because when you release, the reaction force is going in this direction, so the x itself is in this the displacement is negative. Another way to look at it is when the spring constant wise is moving the reaction force. The reaction force for the spring constant is the force itself is towards the negative, okay, because there will be eventually when you pull this thing, there will be a force, okay, there will be a force in this direction, right? So therefore, when you pull this thing, there will be a reaction force. So the reaction force is in terms of the negative side. So it's K, negative K. Similarly to the damping coefficient negative C. Yeah, so you have two scenarios. Either you think that the displacement itself move in the in this direction, moving up, so it's negative. While because when moving up, okay, when moving up, take note that when moving up, the K itself is the reaction force is towards this side now, okay, because when your motion is moving in this direction, your spring constant is trying to resist it from moving up, okay, although the spring is moving but then it's the same thing equals what goes in must come out. So this comes in, okay, so must come out also so this portion is the one that reaction force for whatever thing that accelerated here. So this is why there will be a reaction force due to the, so this is K and this is minus X. So and then similarly in okay, so I think you get what I mean. So this is a very key concept you need to know between the spring constants relationship and the displacement. Okay. So after which we have to define our equation. Okay. Summation of moment. If you remember, summation of moment is where do I find? Is this one. Okay. I mean moment of forces lah. Okay. So the summation of forces for in this scenario, because if you are dealing with moment, you have to have certain data. Okay. Certain angle. In this case, I don't see any angle over here. I only see displacement. So in this case, for displacement, then you have to use yeah. So summation equals to F equals to ma. So if this pause a while. Okay. So using the summation rule, we know that summation of force or the forces equals to ma. Okay. Therefore minus kx minus cx dot. Okay, sorry, I didn't put a dot over here. Is equals to mx double dot. Okay, which is the acceleration, mass acceleration. So this portion is this, and this is this. And then you just bring these two over here. You get this equals to 0. You divide the whole equation by m. You get divide the whole equation by m. So you're trying to make, similarly you're trying to make this coefficient to be 1. So there will be no coefficient that behind this acceleration. So therefore you have this. And then in this case, the damping, we call this okay, hold on a while. So this will be equation 1. Yeah, and then I'm just adding about lah. Okay, but anyway, so after which step 7 is to actually take these equations. Okay, these equations are actually given from when in the test you are given. Okay, you can also memorize, but it's quite easy to memorize, so chillax lah. So apparently you need to memorize or perhaps you refer to this. And so we are taking this and this formula, and then we just plug it in into this thing. And therefore, you can see that k over m is omega n squared, right? K over m is omega n squared because the natural frequency. Just bring the square root over. For damping ratio, this is the damping ratio equals to the damping coefficient, okay, divided by 2m or omega n. Okay, so it's the same formula as this one. Okay, so therefore, if you were to rearrange, okay, you just bring these two omega upwards. You have c over m, right? So c over m can be rewritten as this. And therefore, these are equation 2 and equation 3. And just sub it into equation 1, sub 2 and 3 into equation 1. Okay. So apparently, yeah. And therefore we have this. And this is a linear second order or homogeneous. Now here comes the very tricky part. Okay. You have now you have what do we have? Okay, we have we have two variables over here. We have x and we have our damping factor. Okay. So apparently you can solve for x or you can solve for your damping factor. But however, we want okay, the explanation may not be strong, but I hope I can make it clear is that because we are trying to set this equation in terms of a general equation that that when you sub in your damping factor, you'll get an answer. Okay, so when you sub in maybe I should write down the hold on. So this is the general equation. Later I'll just tell you how it's solved. But this is the general equation. It's in terms of damping factor. I mean the damping ratio, and and the so-called the omega natural frequency. So apparently, trying to set the equation that is relates to the damping ratio and the natural frequency, so that whatever thing that happens in the movement, the motion of the graph itself, the spring itself can actually be written into this equation, and then you can solve for it. So this is our primary concern. So we are not looking into how the graph would look like. Okay, although the after you have this general equation, when you sub it in, you can eventually have equations that can also help us to plot this one. Okay, so for in this, just make clear that this general equation is to help us to derive an answer for x, the displacement. Okay, so that we can solve for the displacement, and then eventually, and the displacement itself is dependent of the damping ratio mostly. Okay, because the natural frequency is is set. Okay, it's typically given to you. You just need to solve k, and that's it. For damping factor, you have to sub in the condition. This is why they always have the subcritical damping, sub damping ratio equals to 1, less than 1, or whatever. So this is the rationale behind why you want to, you know, um trying to make this as a subject. So therefore, for x double dot and this axis, right, we have to sub in our own equations, so that you can actually fit into this theory. So therefore, the variable x that we choose is actually hold on, I write down. Okay, so okay, where am I? Actually, okay, so yeah, okay, let's deem this equation as equation 4. Okay, when you sub all these things inside here. Okay, we last stop here. Okay, and then we say that we explain that why we want to make this okay, you just, yeah, okay, I no need to explain. Okay. Okay, anyway, so sub x as ae rho t. Okay, so we sub this x as ae rho t. Okay, in order to make the damping ratio as a variable. Okay, so this is the variable because um later maybe in the summary of this video. Okay, anyway, I don't know, fuck. Anyway, x equals to ae rho t. And then like x dot is equals to rho a e rho t. You just differentiate one time, differentiate second time, and then you sub all this thing back into this equation. So this is x double dot, and this is x dot. Okay, I didn't change anything. I just sub in all this thing back into this equation. That's all. Okay, and then when I sub this thing back, hold on. Yeah. So just to take note that I already changed this. So just now if you remember it's a e rho t only. So I just put in rho m squared because I forget to put in. And then now we cancel. The next step is to cancel all the a r t. I mean a rho t. Okay. Imagine because they are like a constant, so we can just remove the constants. So we will have rho square plus two zeta omega rho plus this. Now we have a quadratic equation. So if you have a quadratic equation, you can solve using quadratic equation. You can solve using quadratic equation. Okay. So apparently you just sub in minus b plus minus, the typical one. And then one key note is that once you expand this thing, you can actually bring the same terms out. Okay, it's a habit, so you have to bring the same terms out. So the same terms you can see is 4 omega m squared. So when you bring this thing out of the square root, you have to, square root the whole thing out. So for omega n squared becomes 2 omega. Okay, so 4 square root is 2. omega square root is omega. So you just initially you just bring out the 4 omega in square. You just factorize lah. So after which then you have done this one square minus 1. So in other words, I think you just write down lah. If you minus 1 like that, right? And then when you bring this thing out, then it's and then after which you divide by 2. Okay, you divide by 2 because they are the same coefficient, so you have this one. And then this one is so your row, okay, your initial row, okay, this row can be equals to minus this plus or minus. Okay, so maybe I should write down in a more defined way so you can see it clearer. Yeah, so it's either plus or minus, and therefore if you were to come back to here, we sub x as a rho t. So now we can actually have a certain value to describe x. So the x itself is actually ae rho t plus b rho t. Okay, whereby whatever damping factor you put in, you can actually solve for x. So therefore a rho t. So therefore this one we sub in over here, and then the negative side we sub in over here. And this whole shit is a general equation. Yes. Okay. So just to summarize before I end this video, is that at first we actually use the same thing. We understand the movement, okay, and then we draw our free body diagram that states all forces acting on the mass itself, okay. And then you do an equation, summation of forces or moment, depends on the situation now is forces. And then you do up the equation, and then now you because there is C over M and K over M, you have to bring things to sub into this. You don't want it to be divided by something, you want it to be just, some constant sums x dot. So therefore, we change it into this form and this form, and we sub it in, and we have a linear second order homogeneous equation. And then because we have two variables, we have x and we have damping factor, and it's a little tough to see, and therefore and also that a, a lot of things is being described using the damping ratio. Okay, the damping ratio is the key to um how do I say it? Hold on. Okay, x and omega. Okay, x and the displacement x is dependent on the damping ratio. Okay, that's what I'm saying. Okay, so the displacement of the mass itself. Okay, how much it moves. Okay, is all on the damping ratio and the natural frequency of the spring itself, right? So therefore, that's why we have in terms of natural frequency and the damping ratio. And therefore, one method to solve this is actually we sub x as a rho t, okay, and then we differentiate 2 times, and then we just sub in all whatever differentiation back into this equation. So we will have this, okay. Once you have this, and then you clear off all the sin a and rho t, you will get a quadratic equation, which is this. And then you do it up, you'll get this thing, and you just sub in back to your x. Because eventually you want to solve for x, so similar, it's the same thing. So by far, if I have complicated you, now I make it very clear that eventually we have to solve for x. This is our equation. But because we have a damping ratio, okay, that is in our way, we don't know how to solve for it, right? So that's why we want to sub x as this in order to solve for x first. And then once you solve for x, and then you sub back into this equation, and then you can use last time our case 1, case 2, case 3 to solve for your variables, I think. So therefore, this is the step that is in between the transition, because last time in your case 1, case 2, case 3, straight away you take the coefficient and then you solve for x already, right? You solve for what is x. But in this case, our x is different. Our x is dependent on the damping ratio and the natural frequency. Therefore, we cannot do anything. We can only using subbing in A rho t. If you sub wrong x, then you 消掉啦. And then the reason behind why you sub in A rho t is because if you were to know that a lot of things decay exponentially, so therefore similarly the spring itself also decay exponentially. And therefore one safe equation we use is actually A rho t. Therefore you get the general equation. So this general equation is actually provided in your test itself. Okay, but yeah, so it's no. Yeah, sorry, paise. It's not provided. So if they so one I think they may actually call you to derive this general equation. So therefore it is good for you to know. And I hope to see you there. Next video, okay, next video I haven't described it. Next video I'll talk about deriving now we actually talk about the derived general equation. Now we have to clear this and then we have a tutorial question to do. And then this one is a little complicated, so not complicated but rather troublesome, so I'll try to use this one to describe rather than, yeah, so see you there.